When you're trying to solve radical equations, your first step is to get the radical by itself, or to isolate the radical. So in this first example, to get the radical by itself, we need to get rid of this 2 right here. So because we're multiplying by 2, we're going to divide by 2 to get rid of that 2. And now our radical is isolated, or there's nothing on the left side of the equal sign other than the radical. Because this particular radical is a square root sign, to get rid of it, we're going to square both sides. What happens then is that square cancels out with the square root, and we're just left with x plus 1 equals 2 squared, or 4. And when we solve that the rest of the way, we find that x equals 3. You can always check your work by plugging that back into the original. 3 plus 1 is 4. The square root of 4 is 2. 2 times 2 is 4. So it works. The next example is very similar, but it's a cube root sign instead. We need to isolate the radical first, so we're going to add 1 to both sides to isolate this cube root sign. And then once the radical is isolated, now we need to get rid of that cube root. To undo a cube root, we are going to cube both sides of the equal sign. The cube and the cube root would then cancel each other out. And then we're left with 2x minus 9 equals 3 cubed, or 27. Then we're going to solve this problem the rest of the way. Add 9 to both sides to get 36. X equals 18. All right, here are a couple more examples. Same idea. This first one, we're going to add 9 to both sides to get started. To get 3. Our cube root is isolated, so we're going to cube both sides so that the cube root and the cube cancel each other out. X equals 3 cubed, or 27. Other one, the square root is already isolated, so we're going to square both sides so that the square and the square root cancel each other out. X plus 25 equals 2 squared, or 4. Which means that x equals negative 21. When there are x's on both sides of the equal sign, you can have extraneous solutions. Now, your solving steps are still the same. We're going to start by just solving for x, but then when we get our final answers for x, we do need to plug those back into the original equation to make sure that they are actually true. You can do all the work correctly and still get extraneous solutions. So on this first example, we're going to get rid of this radical that's isolated by squaring both sides. Remember, when we square x plus 1, that's x plus 1 times x plus 1. Make sure you distribute that all the way out so you don't lose your middle term there. And on the other side, the square and the square root cancel each other out. So when I multiply this all out, what we'll get is x squared plus 2x plus 1. So when we're solving this particular problem, we have a quadratic because of this x squared. So to solve a quadratic, we need to make everything equal 0. So I'm going to move everything to the left side of the equal sign. So x squared minus 5x minus 14 equals 0. And my favorite way to solve a quadratic is by factoring, as long as it's factorable. If it's not factorable, you would have to use the quadratic formula. But this one is factorable. So we get two answers, x equals 7 and x equals negative 2. But like I said before, when you have x's on both sides of the equal sign, you do have to plug those back in to make sure that you don't get an extraneous solution. And in this case, negative 2 is going to be extraneous. So it's not actually a solution to this problem. Only 7 works when we plug it back in. If you plug in negative 2, on the left side of the equal sign, you get negative 2 plus 1, which is negative 1. And on the right side of the equal sign, you would get the square root of -14 plus 15, or the square root of 1, which is 1. And -1 does not equal 1. That's why -2 does not work as a solution. So we'll go through the second example a little bit faster. We're going to start by squaring both sides of the equal sign. So x plus 3 squared, when I multiply x plus 3 times x plus 3, I'm going to get x squared plus 6x plus 9. And on the left side, I just have 10x plus 9 when the square root and the squared cancel each other out. This time I'm going to move everything to the right side of the equal sign. When we have quadratics, I like to keep the squared term positive, and the x squared term was positive over here on the right side. I like to do that because it's a little bit less work than when we go to factor. So because that plus 9 and minus 9 cancel each other out, we just have x squared plus 4x. So I can factor that by factoring out a GCF, which means my two solutions are 0 and 4. But once again, we need to plug those back into the original and make sure that they work. When I plug in 0, I get the square root of 9, or 3 equals 3. That's true, so 0 is a good solution. And when I plug in 4 to both sides, I get the square root of 49 on the left side, which is 7, and I get 7 on the right side. So in this case, both of those are good solutions. So two examples where we have radicals on both sides of the equal sign. In this first example, we can square both sides to get started. And the square roots and the squareds will just cancel each other out. So we have 2x plus 5 equals x plus 7. And when we solve that, we get x equals 2. A quick check tells me that 2 is a good solution. We get the square root of 9 equals the square root of 9, which is true. But the second example is a little bit trickier, because when we square both sides of the equal sign, we end up needing to FOIL the left side of the equal sign. So we'll have the square root of x plus 2 plus 1 times the square root of x plus 2 plus 1. And then on the right side, the square root and the square just cancel each other out. So we have 3 minus x. But because this square root side wasn't isolated, that's why we have to FOIL this all out. So when I take the square root of x plus 2 times the square root of x plus 2, that's just the square root of x plus 2 squared, or x plus 2. Then I have the square root of x plus 2 times 1. I'm going to put 1 times the square root of x plus 2. We get that a second time. And then 1 times 1 is 1. All right, I'm going to combine my like terms now. So I have 2 times the square root of x plus 2. I have an x over here. I have this constant and this constant combined to make 3. And then we're going to solve like we did at the very beginning of these notes, where we need to isolate now the one radical that's left. This is our only radical left. We need to isolate that. So I'm going to start by subtracting this x and this 3 over. So I have 2 times the square root of x plus 2 equals negative 2x. Still not isolated. I need to divide both sides by 2. Now my radical is isolated, so I can square both sides. So when I square both sides, this negative x squared is just x squared. I'm going to make it equal 0. I'm moving everything to the right side so that my squared term can stay positive. This is factorable. And so we get two solutions, x equals 2 and x equals -1. But because we had variables and an x on both sides of the equal sign, we do need to check to make sure that neither one of those is extraneous. So when I plug in 2 to both sides, I get the square root of 4 plus 1 on the left side, or 2 plus 1, which is 3. And on the right side, I get the square root of 3 minus 2, or the square root of 1, which is 1. Well, that doesn't work, so that must be extraneous. But when I plug in -1, I get the square root of 1 plus 1 equals the square root of 3 minus -1, or 4. So 2 equals 2. That one is a good solution. All right, the last thing we're going to talk about is how to solve when we have rational exponents. Remember, rational exponents are just a fancy way of writing radicals. So they kind of work similarly. First, we're going to isolate whatever has the rational exponent. So in this first example, we are going to subtract 2 to both sides to isolate it. And then we're going to use some exponent rules here. I'm going to raise this to the power of 2/3 in order to get rid of that exponent of 3/2, because our exponent rules say when you raise a power to a power, you're multiplying them, and 3/2 times 2/3 is just 1. But if we raise the left side of the equal sign to the power of 2/3, we need to do the same thing to the right side. And 8 to the 2/3 power is the same thing as the cube root of 8 squared, or cube root of 8 is 2. 2 squared is 4. So I have 2x equals 4, which means that x equals 2. Let's do another one. So on this one, we're getting rid of an exponent of 1/2. It's already isolated. So I'm going to raise both sides to the power of 2/1, or just 2. The reason we do that is because a power to a power, you multiply the exponents. So our new exponent over there is 1. So we're just left with the x plus 30. But on the right side, instead of x, now it's x squared. This one's a quadratic, so we do need to make it equal to 0. I'm going to move everything to the right side of the equal sign. It's factorable. X equals 6 and x equals -5. Because we had x's on both sides of the equal sign, we do need to check for extraneous solutions here. So if I plug in 6 on the left side, I get the square root of 36, or 36 to the 1/2 power. That means the same thing, which is 6. So that is a solution that works. When I plug in -5 to both sides, I get the square root of 25 equals -5. Well, the square root of 25 is 5. So that would be an extraneous solution. And then last two examples, same idea. This first one, we're going to raise both sides to the 3/5 power to cancel out with that 5/3. So when I do that, I have the 5th root of 243, or 3 cubed, which is 27. Add 5 to both sides to get 32. And over here, I need to isolate it first by subtracting 3 from both sides. Always isolate those exponents or radicals first. And then to get rid of a 1/3 power, I'm going to raise both sides to the power of 3/1, which is 3. So I get x plus 2 when those exponents cancel each other out, equals 4 to the 3rd power, or 64, which means x equals 62.